everyone. Today I am going to introduce you the topic that is stone column, which is already known to you, but just because of revision, we are giving some time, or we are again repeat the topic, and then we have to see the design parameters of the stone column. So, to learn the design parameters in this topic, we have to recall the some theoretical portions. That's why we have to again follow some important theoretical points. So my first point is nothing but about the introduction of the stone column. When we talk about the stone column, you know that it is a technique which is improve the both type of soil, that is cohesive as well as silty sands, to increase the strength and to decrease the compressibility of the soil. Then second part, stone column can improve the soil deposit by densification, reinforcement and drainage functions. Always remember, when you are going to adopt the technique that is stone column, how the stone column can improve soil with the deposit of three terms, that is D, R and D, or D square and R. How it is? First is it is nothing but the densification, second is the drainage function, and thirdly reinforcement. Now, out of several techniques available for improving soft clay stone columns are ideally suitable for the structure with widespread loads. In case of soil having a medium to low shape bearing capacity, ground improvement with the help of stone column have been found economical and faster in the construction. The main aim of soil improvement is to increase the shear strength, loading capacity, stability and the settlement controls. So these are the main aim of the soil improvement, is to increase the shear strength of loading capacity, stability and settlement control. Now what are the stone column? Stone column technique is also known as Vibro replacement or Vibro displacement, is a ground improvement technique where vertical columns are compacted, aggregates are formed through the soil to be improved. This is nothing but the stone column, and always remember, stone column is also known as Vibro replacement or the Vibro displacement also. Next is the advantages about the stone column. Firstly, the stone column help in improving slope of both embankment and the natural slope. Okay, if there are both embankments are present, the stone columns are improve the both type of embankment and the natural slope on the present present on the ground. Second, bring granular means very small and free drainage. Consolidation settlements are accelerated and post compaction settlements are minimized. Increase in the resistance of soil to liquefaction, reduction of the foundation settlements, and increase in the load carrying capacity. These are the advantages about the stone column. Then the stone column can be resist a lateral load, and construction is very simple and cost effective. Then these are the stone column combine at least four different mechanisms to improve of a liquefiable soil deposit. So which are these four different mechanisms that we have to see? First is a stone column improve the deposit by virtue of their own high density, strength and steepness. It improves deposits of their own high density, strength and steepness. Then it provide a closely spaced drainage boundaries that inhabit the space is more while you are going to use these techniques. For the development of high excessive pore water pressure, the space is needed to development of high excess pore water pressure. Then this process by which stones column are installed densify the soil surrounding by combined effect of vibration and displacement. In this process by which stone columns are installed, which densify the soil surrounding by the combination effect or the combined effect of vibration and displacement. The installation process increase the lateral stress in the soil surrounding the stone column. So this is all about the stone columns. So stone columns in a saturated cohesive soil work as a drainage system and resulting in decrease in consolidation time. Stone column system in soft compressible soils are like a pile foundation. Expect that pile caps, structural connections, and deep penetration to underlying firm strata are not required. So, in the stone column, if you are going to use the stone column technique to improve your ground in a saturated cohesive soil, it work as a pile foundation. So now this is the very important topic, that is basic design parameters. So while we talk about the basic design parameters, so first is nothing but the stone column diameter. So installation of stone column in a soft cohesive soil is basically a self compensating process that is softer than the soil. Bigger is the diameter of the stone column formed due to the lateral displacement of the stone during vibrations or the ramming. The compacted diameter of the hole is always greater than the initial diameter of the probe, or the casing, depending upon the soil type, is undrained shear strength, stone size, characteristics of the vibrating probe, rammer use, and the construction method. So always remember, installation of stone column in the soft cohesive soil is basically soft compacting process. Secondly, the due to the lateral displacement of stone, vibrations or the ramming, the complete diameter of the hole is always greater than the initial diameter. Okay, this always greater than the initial diameter of the probe or the casing, depending upon the soil. Next is the approximate diameter of the stone column is the field may be determined from the known compacted volume of material required to fill the hole of a known length and maximum and minimum of the known length and maximum and minimum densities of the stone. So this is all about this. Then the patterns. Stone column should be installed preferably in equilateral triangular pattern which gives the most dense packing, although a square pattern may also be used. The pattern of this stone column is nothing but equilateral triangular pattern. How this pattern is look like, that we have to see in the next slides. Then about the spacing. The design of stone column should be a site specific. The design of stone column should be a site specific and no precise guidelines can be given on the maximum and minimum column spacing. However, the column spacing may be broadly range from 2 to 3 depending upon the site conditions, loading pattern, column factors and installation technique, and it is also depend upon the settlement tolerance, etc. For the large type of project, it is desirable to carry out the field trial to determine the most optimum spacing of stone column, taking into the consideration the required bearing capacity of the soil and permissible settlements of the foundations. So see here, these are the figures of various patterns of stone column. First is triangular arrangement of the stone column, and second is square arrangement for the stone column. Okay, if you look, this center to center distance between these two columns is nothing but the pile spacing. The center to center distance between these two columns is nothing but the pile spacing, and this is the triangular arrangement of the stone column. This is nothing but the square arrangement. Again, the center to center distance is nothing but the pile spacing, and the diameter is represent as d suffix e. This is the various process. Then the equivalent diameter. The tributary areas of the soil surrounding each stone column form an regular hexagon around the column. The tributary area of the soil surrounding each stone column forms a triangular hexagon around the column. It may be closely approximated by a equivalent circular area having the same total area. The equivalent circle has an effective diameter, that's why it is called as d suffix e. Why it is called as d suffix e? See here, it is nothing but the equivalent diameter, that's why it is called as d suffix e, which is given by these following equations, that is d is equal to 1.05 S for the equivalent pattern and D is equal to 1.13 into S, that is for the square pattern, where what is meant by S? The S is nothing but the spacing of the stone column. Now the estimation of the load carrying capacity of a column. So stone column in a cohesive soil. So load capacity of the treated ground may be obtained by summing up the contribution of each of the following component for widespread loads such as tanks and embankments. So first of all, capacity of the stone column resulting from the resistance offered by the surrounding soil against the lateral deformation, that is nothing but the bulging under the axial load, that is your Q1. Then what is Q2, Q3, that we have to see in the detail. The capacity of the stone column resulting from increase in a resistance. The second stage is increase in a resistance offered by the surrounding soil due to the surcharge over it. And third step is nothing but the bearing support provided by the intervening soil between the columns. So this is about the first, second and third step. In the first step, we have to calculate the capacity of the stone column resulting from the resistance offered by the surrounding soil against its lateral deformation, and that lateral deformation is also called as bulging under the axial load. Okay, so axial load is nothing but the load which is act on axis. That then the second is capacity of the stone column resulting from increase in the resistance offered by the surrounding soil, and third is bearing support provided by the intervening soil between the columns. Now the capacity based on the bulging of the column, the foundation soil is at a failure is stressed horizontally due to the bulging of the stone column. Then the surcharge effect. Initially, the surcharge load is supported entirely by the rigid column. As the column dilates, some load is shared by the intervening soil depending upon the relative rigidity of the column and the soil. Consolidation of the soil under this load result in the increase in the strength which provided additional lateral resistance against the bulging. Okay, if suppose the consolidation of the soil under this load result into the increase its strength which provided additional lateral resistance to the bulging. Then second point about the surcharge effect is nothing but the surcharge load may consist of sand blanket and sand pad being applicable for the tank foundations only. If there is tank foundations which is given in your problem, at the same time you have to think about the surcharge load which may consist of sand blanket and sand pad. If thickness of these elements are not known, the limiting thickness of the surcharge loading as represented by the safe bearing capacity of the soil may be considered. The increase in the capacity of the column due to surcharge may be compacted in terms of increase mean radial stress of the soil. So it is in which case only it is applicable for the tank foundations only. Then the surcharge effect is a minimum at the edge. It should be compensated by the installing additional columns in the peripheral region of the facility. Being supported provide as an intervening soil. The component consists of hysteretic capacity of the virgin soil of support a vertical load which may be compacted as follows. The effective area of the stone column including the intervening soil for the triangular pattern is 0.866 S into S. So these are the nothing but the equations. So first of all, this Ag is given by the following formula. So that is 0.866 into S square minus pi into D square divided by 4. The safe load taken by the intervening soil is nothing but the Q3 is equal to Q safe into Ag. Ag is nothing but what? 0.866 into S square minus pi into D square divided by 4. Now overall safe load of the each column that you have to know, that is Q1, Q2 plus Q3. Make an addition of all this and you will get the overall safe load on each soil. Next is the design calculations. Design calculations should be repeated till there is a coverage of the assumed and calculated column spacing. design calculation you have to continue up to you will get assume calculated spacing of the stone column. One or two trials may be required to achieve the acceptable degree of convergence. Okay, you have to take one or two trials for the same. Additional stone column may be required inside and outside the periphery of the loaded area considering pressure, distribution, presence and absence of the surcharge, and permissible or expected settlement of the structure. These additional columns may be provided either as a rings or at a closer spacing for an approximate or appropriate distance inside as well as outside the periphery of the loaded area. So this is all about this how to calculate and all. Now the failure mechanism, it is very important. Question may be asked on the this topic for the university examination point of view for up to the 5 to 10 marks. So what is the failure mechanism? See here, the failure mechanism of a single stone column is a homogeneous soil loaded over its area significantly depend upon the length of the column. For columns having the greater length than its critical length, that is about 4 times than the column diameter, and irrespective whether it is end bearing or floating, it fails by bulging. In the next slide we have to see the different type of figures, and in that figure there is a failure mechanism. However, columns shorter than the critical length are likely to fall in a general shear if it is end bearing on the rigid base, and in the end bearing if it is floating column as shown in the figure. Whenever a stone column is usually loaded over an area greater than its own, in which case is experienced significantly less bulging leading to the greater ultimate load capacity and reduced settlement since the load is carried by both of the stone column and surrounding soil. So these are the conditions about failure mechanism of single stone column in a homogeneous soft layer. If you observe the first figure that is named as 2a, second figure is 2b and third figure is 2c. First of all we will talk about the figure number 1, that is 2a, which is nothing but longer stone column with a firm or floating support bulging failure. If you observe that first from the ground level to the from this ground level to certain distance, the distance is 2d, and from ground level to the full portion of the failure it is 4d, and the distance between this capital D is nothing but the entire diameter of that stone column. Second is figure number 2b, which is nothing but short column with the rigid base, and that figure is for the shear failure. Okay, and third is short floating column punching failure, that is the side friction and end bearing which is present in this figure. Now this different types of loading applied to the stone column. So the different types of loading, see here the entire load is applied on the stone column only in second figure, and here in the first figure the load is applied on the both side of the column and also the stone column. So whenever interlaying of the sand and clay occurs, effective reduction in the settlement may be brought about the carrying out the treatment of the stone column through the compressible layers. Secondly, when clay is present in the form of lenses, and if the ratio of the thickness of the lens to the stone column diameter is less than or equal to 1, the settlement due to presence of lenses may be insignificant. In the mixed soil, the failure of stone column should be checked both for the predominantly sandy soil as well as the clay soil, the governing value being lower of the two calculated values. Then these are the factor influencing Vibro floated stone columns. Actually this portion is not present in your syllabus. Directly we will goes to the conclusion what we studied from this lecture, that is stone columns help in improving slopes of the both, that is embankment and the natural slope, then bring granular and free draining consolidation settlements are accelerated and post compaction settlements are minimized. Next, increase in the resistance of the soil to the liquefaction, reduction of the foundation settlements, and increase in the load carrying capacity. Stone columns can also reduce the lateral load, and construction is a simple and cost effective. Then these are the reference: soil engineering, this is the book. Then the foundation analysis and design by Joseph, foundation design by Nainan, and these both IS code are very important. IS 15284 part 1 2003, design and construction for the ground improvement guidelines part 1, stone column, and second is IS 1301992, ground improvement techniques on the weak soil. Tomorrow we are going to start with the numerical, which is dependent upon the topic, that is stone column. While we solve the numerical, you will easily get the idea about this desirable theory and all matter of this theory in the detail. Thank you for your patience.